Today's customers are more knowledgeable than ever in terms of vehicle operation. The sales professional has to be familiar with how the various components of a new car or truck work and why they've been designed the way they are in today's Chevrolet products. The following disc program breaks down vehicle operations into 6 major areas: energy, power transfer, and aerodynamics on side 1, handling, weight management, and space utilization on side 2. Each of these areas is examined in terms of present-day technology and application. Energy, unharnessed, powerful, explosive. Energy of such magnitude that it transcends the frigid darkness of space through millions of miles to warm our planet and sustain life forms. And within these life forms, this energy of the sun is stored. And even after they die, the energy remains for eons underground. The energy is stored in various states: solid, gas, liquid, all with the ability to unleash the power of the sun through combustion, burning. And with coal, a solid substance, fire will ignite it. The same is true of its gaseous state. But with crude oil, combustion's a little more complicated. Crude oil will not readily burn until it's been refined. This results in gasoline, a product capable of sustaining usable combustion. The energy stored in just this amount is equivalent to the explosive force of a stick of dynamite. This combustion can only take place, however, in the presence of oxygen. Gasoline is, by its nature, volatile. It readily combines with air, forming a highly combustible mixture that can unleash tremendous power. This power is harnessed by the internal combustion engine and converted into rotary motion that's needed to move our vehicles. The internal combustion engine has been around for a long time, and while other designs have been explored, they've yet to prove themselves superior in terms of efficiency and dependability. And over the years, engineers have found many ways to make it better, more efficient, and more economical. One of the most critical areas of research involves the combustion itself. Now, this is particularly important because only 15% of gasoline's potential energy is used to power the vehicle. Most of the energy is lost through heat dissipation and exhaust gases. The quality of combustion, that is, the power generated from it, depends on the mix of fuel and air. Too much fuel makes the mixture rich, while not enough is a lean condition. The result from either circumstance is the same: inefficient combustion, poor use of fuel, and sacrifice of power. One of the main thrusts of research and development has been to find ways to control the air-fuel mixture more efficiently. Engineers realized that the conventional carburetor systems were physically limited in their ability to monitor this mixture. So they pursued new avenues of research. Reaching into the world of microprocessor technology, they developed a computer capable of analyzing data at thousands of calculations per second. This allowed them to design a system that determines the correct air-fuel mixture with the necessary accuracy to maximize combustion throughout the engine's performance spectrum. The computer must rely on data, such as engine speed and exhaust gases content, to make the correct determinations. This data is fed by a system of sensors, which is processed and fed back to control devices on the engine and transmission. A great deal of data must be processed, even for the simplest engine functions. Take idle speed as an example. The computer receives inputs of engine coolant temperature, battery voltage, vehicle speed, engine speed, air conditioner on-off status, transmission in gear or neutral status, throttle position, manifold pressure, and whether the starter is cranking. It analyzes this data and signals the idle speed motor to position the throttle to provide proper mixture for the operating condition. This system has introduced new standards of precision and accuracy, made possible with the advent of computer technology. And this is only the beginning. As we look to the future, microprocessor technology will account for even greater applications in the management of our car and truck systems. With the introduction of microprocessors that can control functions at high rates of speed, engineers began developing fuel control systems that could respond accordingly. Well, electronic fuel injection is just such a system. It precisely meters the correct air-fuel ratio by responding to on-off commands from the computer. The number of on commands the injector can get from the computer determines the precise amount of fuel entering each cylinder. Now again, the computer monitors the conditions of engine load, RPM, and the amount of oxygen in the exhaust gases before calculating the number of pulses required. Efficiency has long been a hallmark for another type of internal combustion engine, the diesel. Diesels share many characteristics with gasoline engines, such as cylinders, pistons, and valves. But there are key differences in a diesel, such as fuel injectors, pre-combustion chambers, electric glow plugs, thicker walls, and heavier duty components to withstand the tremendous heat and pressure. To better understand the differences between the gas and diesel engine, let's first see how the gasoline engine works. On the intake stroke, a mixture of both gasoline and air is drawn into the cylinder. On the compression stroke, this mixture is squeezed to about 1/8 of its original volume. At the beginning of the combustion stroke, this highly volatile mixture of gas and air is ignited by the spark plug, and the explosion forces this piston down. The diesel engine burns fuel in a different and more efficient way, without the use of a spark plug. At the start of the combustion cycle, the cylinder is filled with only air as the piston moves downward. This air is then compressed by the piston to 1/22 of its original volume, generating tremendous pressure and heat, approaching 1,000 degrees Fahrenheit. The less volatile diesel fuel is then injected, and because of the extreme heat of the compressed air, ignites instantly without the use of a spark plug, burning evenly and completely. Diesels are known for their economy and efficiency, but what accounts for that? What makes this engine more efficient than its gasoline counterpart? Well, part of the answer is the higher energy content of diesel fuel. Compared to gasoline, diesel fuel has 12% more heat energy. A diesel engine also allows for more efficient combustion. Because diesels draw only air into the cylinder, there's usually more air present during combustion. Now, this fact, coupled with the greater compression ratio of the diesel, means that the engine is able to make more complete use of its fuel. Overall, diesel engines average 30% greater fuel economy than comparable gasoline engines. Microprocessors, electronic fuel injection, diesel technology. These are some of the ways the internal combustion engine has been made more efficient. But what about power? There are ways of extracting more power from a given engine size. One of these is turbocharging. What is a turbocharger? Well, it's nothing more than a sophisticated blower which is driven by turbine blades. The engine's hot exhaust gases are used to power the blades. The turbocharger pumps more air into the engine's cylinders, thereby increasing the concentration of air and fuel. This results in more power from the same displacement. This system captures the energy in the exhaust gases that would otherwise be lost and transforms it into additional power. Making the internal combustion engine more efficient and more powerful. These are important steps in meeting today's challenges. In addition to the challenges of greater fuel efficiency, there are other considerations for automotive engineers, including controlling exhaust gases. Now, some time ago, exhaust gases were identified as major contributors to air pollution, particularly in areas with heavy vehicle populations. Engineers developed two basic methods of controlling emissions. One way is to make the combustion cleaner or more efficient. Another is by cleaning up gases released through the exhaust. Both approaches required extensive modification of the engine and exhaust system. One of the major breakthroughs of this effort was the development of a new device built on an old scientific principle, a catalytic converter. In many of today's vehicles, three-way converters are used. This type is made up of honeycombs coated with three rare metals: platinum, palladium, and rhodium. These metals are the catalysts that promote a chemical reaction without being permanently changed themselves. The converter controls the three principal emission components: hydrocarbons, carbon monoxide, and nitrous oxide. Through its catalytic action, it changes carbon monoxide and hydrocarbons to carbon dioxide and water. Also, the catalyst changes the nitrous oxide to nitrogen and oxygen. All are principal components of the air we breathe. These complex chemical reactions will only take place if the air-fuel mixture in the combustion chamber is in exactly the right proportions. This is constantly maintained by the onboard microprocessor. By fine-tuning the engine, combustion is maximized so that today's engines are not only cleaner, they also use fuel far more efficiently than engines of 20 years ago or more. Well, for example, emissions from the typical 1960 Chevrolet went uncontrolled. Virtually 100% of all spent gases went unchecked. Significant improvements have been obtained by 1974, the year prior to the introduction of the catalytic converter. Yet when the computer and converter technologies are joined together, today's Chevrolets, on the average, emit 96% fewer hydrocarbons and carbon monoxide, and 76% less nitrous oxides than their 1960 forebearers. This is a true American success story. Extracting more power from less displacement, marrying the internal combustion engine to the microprocessor, state-of-the-art technology in fuel delivery systems. What lies ahead in our quest for greater efficiency? Well, after harnessing the power of the sun, who knows what limits there are to man's ingenuity? While harnessing of the engine's power is important, transforming it into a usable form is just as critical. This is true of all modes of transportation. What's really happening here? The bicyclist's body is burning calories of energy as his legs provide the power to turn the crank connected to the chain sprocket. He is, in effect, the engine that powers this machine. And right now, the effort is rather comfortable. The road is smooth, the terrain is flat, and he's moving right along. Under these conditions, the gearing between the engine, the cyclist, and the load conditions of this machine are in harmony. That's fine, as long as the road is flat. But when he starts up an incline, he begins working harder and overheating. What's the solution? Simple. He just selects another gear. Now he's not working as hard, even though he is pedaling faster. The principle at work here is torque. But what is this force? Let's take a closer look. Out on the flat road, the gearing of the bicycle was set up to maximize speed. Now notice that the gear that's attached to the pedal is several times larger than the one that's attached to the rear wheel. The result is fewer turns of the large gear in relation to the smaller one. In other words, the wheels of the bicycle turn faster than the gear that drives them. Now, in power transfer terms, this maximizes cruising speed, but offers very little torque or power to climb hills or accelerate. That's why the cyclist had to change gears. But what really happened? Did he suddenly get stronger? No. He compromised. He gave up speed for torque, and he gained the ability to climb the hill. The relationship of the two gears changed. Now the driving gear is smaller, and the driven gear is larger. Now this means there's an increase in pedal turns and a decrease in revolutions at the rear wheel. or less speed. But though there's less speed, there's more power or torque. This is the same process and principle that takes place in a car or truck transmission. This is where the power of the engine is harnessed and the torque managed. From a standing start, the engine engages with the transmission in low gear to produce lots of torque, to overcome inertia and provide acceleration. Intermediate gear provides a little less torque, but builds speed. In certain Chevrolet transmissions, 2 or more intermediate gears provide greater torque and speed flexibility. In high gear, or final drive, the engine and transmission output speed is the same. Torque requirements are minimal, and the vehicle speed is at cruising. Should the vehicle encounter a steep hill, its speed would decrease. Increased torque would be required to climb it, and the transmission would shift to an intermediate gear to compensate, just as the bicycle rider did. On a stretch of flat road, some transmissions have an available overdrive gear that allows the engine to turn fewer revolutions than the drive shaft. Overdrive results in better fuel economy and less engine noise. When torque is required, a downshift to a lower gear is necessary. Now, in order to change gears, we need some way of disengaging the direct connection between the engine and the manual transmission to allow the gears to slide and mesh with each other, and to move the vehicle from a standing start smoothly. The device designed to accomplish this task is the clutch. Essentially, the clutch is a sandwich of friction material between 2 round plates, one connected to the engine, the other to the transmission. Both are engaged by heavy springs that can be released gradually to move the vehicle from a stop. When the clutch is fully engaged, there's a mechanical connection between the engine and the transmission. An automatic transmission uses the principles of hydraulics for a smooth transfer of power between the engine and transmission without the need of a clutch. A fluid coupling, better known as a torque converter, is used. Now, this is essentially 2 sets of fan blades facing each other in a petroleum fluid. As the driving fan attached to the engine rotates, it pumps fluid into the driven fan attached to the transmission, causing it to rotate. Because there's no direct mechanical connection between the two, there is slippage between the driving fan and the driven fan. This slippage is required for gear changes during acceleration, but it can be a source of wasted power at cruising speeds. Engineers evaluated the situation and came up with the best of both worlds, the torque converter clutch. Above certain cruising speeds and under specified load conditions, the torque converter clutch engages automatically, providing a direct link between the engine and transmission. This link allows 100% power transfer from the driving fan to the driven fan. When speed or torque requirements change, the clutch disengages, the torque converter resumes its normal fluid coupling mode. Automotive research is aimed at even greater advances in transmission efficiency with something called the continuously variable transmission. In this unique system, the engine speed would remain constant. The necessary torque for acceleration and gearing for highway speed would be provided by the transmission. Now think of it. Instead of accelerating the engine to gain speed, you merely change gears. It's an extremely efficient way of transferring engine power and conserving energy. And it's something we can all look forward to. General Motors wind tunnel. Considerable investments in terms of dollars and man-hours have been made here, studying the effects of air moving over a vehicle. This is the laboratory where the science of aerodynamics is applied to the design of tomorrow's Chevrolets. Why the investment? Because in terms of increasing a vehicle's efficiency, no other factor has as great an impact or degree of control as aerodynamics. Moving through the air exacts a cost. The difference between 20 miles per hour and 60 requires 27 times the horsepower. At 55 miles per hour, more than half of the vehicle's power is used to overcome air resistance. At 70 miles per hour, the power required is almost doubled. Any design improvement, any adjustment of body contours that helps the vehicle slice through the air a little easier means increased efficiency. You see more of this influence every day on all sorts of vehicles, and the future holds a great deal more. Aerodynamics is the study of how air moves over the surface of an object. The more aerodynamic a vehicle's shape, well, the less it has to work to overcome the air's resistance. The vehicle design process begins with an analysis of basic shapes and the aerodynamic efficiency of each. The measure of this efficiency is expressed in the term coefficient of drag, or CD. When placed in a stream of air, geometric shapes all have predictable coefficients of drag. The number can range from 1.8 for an aerodynamically inefficient cube to 0.005 for one of the most efficient shapes, the airfoil. But when these shapes are applied to vehicle designs, we find some remarkable contradictions. For example, how can it be that this large van has the same coefficient of drag as this small sedan? Because this number doesn't take into account the vehicle's size, in particular its frontal area. This refers to the vehicle's total area presented to the flow of air, a cross-section of the vehicle's front view at its highest and widest point. Why is this important? Because frontal area is a major component of the vehicle's total drag as it moves through the air. That's why a vehicle with a big frontal area can often have an impressive coefficient of drag number, but still consume large amounts of energy needed to overcome its overall drag at highway speeds. A very large part of the downsizing effort in today's vehicles is to keep this frontal area to a minimum, as well as enhancing the design to part the air smoothly. Some of the findings made during wind tunnel testing can result in subtle yet effective enhancements to vehicle design. Sharp lines along fender edges are detrimental, and even minor things like mirrors or gaps between the doors and fenders affect the vehicle's aerodynamic efficiency. Open side windows can increase drag by 10% during highway driving. A wedge shape can help reduce overall drag. The angle of the windshield is a critical factor. A steeper angle helps minimize drag. Angling the vehicle downward about 1 degree is optimum for increasing aerodynamic efficiency. The addition of a rear deck lead spoiler also reduces drag. The use of a front air dam significantly reduces drag and lift by reducing air pressure under the vehicle, where turbulence is great. This turbulence is caused by an irregular underbody configuration. Channeling air around the vehicle thereby reduces air breakup and turbulence. Ideally, a vertical air dam should completely shield the front tires and have minimal ground clearance. Aerodynamic drag affects other vehicle performance factors besides fuel economy. A good aerodynamic design also contributes to a quieter ride because wind noise decreases. Windows will be cleaner because there's less road dirt accumulated, and there'll be greater vehicle stability in crosswinds. It even improves traction by creating a downward force, counteracting the natural tendency of most vehicles to increase lift at cruising speeds. The science of aerodynamics applied to vehicles is just beginning to make great strides in developing styling philosophies that mirror efficiency and economy.